welding, painting, assembly, testing, gauging, inspection. A lot of industrial processes have been robotized, and it is independent of humans. And there are also applications where humans can work along with robots. And there is a new concept, and it is called as collaborative robots, or short-term cobots. So that forms the industrial robots. And coming to the service robots, we have robots for surgery, robots for underwater applications, robots uh, for space, robots for like unmanned aerial vehicles, robots for assisting humans, robots for taking care of patients, robots for navigation, robots for entertainment, robots for teaching. So various applications now robots have come. That was a small, there were small groups, so that is why it was, they were all clubbed together and we called them as service robots. Whereas industrial robots, it was much more, it is more saturated right now. There are standard configurations, and all the robots fall in this group of industrial standards. But service robots are huge, from humanoids to small mobile platforms. It's the market as well as everything is huge. So there's a wide spectrum. And if you see the growth of industrial robots, I'm showing from 2018 to 2025 with some expected volumes. Because of COVID, there is a small dip, but apart from that, after the post-COVID scenario, the trend is still going to be, the demand is going to be high. And 48.7 billion US dollars was the worth of this industry in 2019. And the prediction is that by 2024, we will have about 75.6 billion US dollar. That is going to be uh, the market for industrial robots. So that's a big market. Uh, but when we take the service robots industry, in 2016, here you can see the one in blue is industrial, the one marked in gray is service robots, and green is the total volume of robots sold. So in 2016, you can see the number of pieces industrial robots sold as well as service robots. In 2017, there is 124% growth in terms of service robotics industry, whereas it was 32% for industrial robots. You can see the growth. So it is a huge growth, like in service robots industry. So 2020, it is almost, the market for service robots is as good as or as high as industrial robots. So the total robotic industry world over has grown by 19% compared to the previous year, compared to 2019. And the expected growth in 2020 for uh, service robotics is 37 billion, as well as for 2025 the projection or prediction is that 102.5 billion. So that is another big industry that is growing up. Now coming to our topic today is about the configurations or the architecture of industrial robots. So in this particular FDP, at the end of the FDP, I think we should have enough knowledge on various types of industrial robots, its configuration, various kinds of end effectors, how to size end effectors, how to design end effectors, how to customize end effectors, how to integrate a robot and an end effector, and also to integrate robots to a shop floor with some examples on programming these robots. And that is for the first week. Second week, we will have the autonomous systems. That talks more about the service industry or service robots. So the first week will be more concentrated on the industrial robots, and the second week will be more focused on service robots. And when it comes to service robots, navigation is very important. So about mostly on the mobile platforms and AMRs. So we have excellent speakers for all these sessions. Please attend, take notes, make questions, discuss. Hopefully we can form a WhatsApp group if you are interested and post your questions or discussions. So that can make the group more lively, and sharing of knowledge will happen through that. Okay, coming to the anatomy of robots. Fundamentally, an industrial robot looks like a human arm. So we have two arms, but most of the industrial robots are having only single arm. Uh, so this human arms are made up of, you know that. We have bones, we have joints, like shoulder. We have various joints and we have bonds that connects between each joint. Similarly, an industrial robot, what we can see here is an articulated configuration that also has links and joints. Simply, an industrial robot configuration has links and joints. The mechanical structure has got only links and joints. A link is like a human arm's bonds. It links between two joints. So one joint will have minimum two links. So one may be fixed, one may be movable. In some cases it's like that. So but it just replicates a human hand. Mechanically it replaces, or it is equivalent to our bones or muscles. Muscles power our links. So we need blood supply, we need commands from the brain, we also give a feedback. So all these things are incorporated into a manipulator. That is how a robo manipulator, it is fundamentally a replication of a human hand. So all of you will be able to design, develop robotic manipulators. So what is that you should understand? We should understand some of the robotic terms before we start building or designing robo manipulators. As technology has improved, a lot of resources are there, a lot of softwares are there where in fact you can just drag and drop. So you can have joints, links, all ready-made available, or you can also design on your own based on the reach you need, the payload you need, the degrees of freedom. So all these things can be designed by yourself. So joints provide relative motion. So a link is a rigid member between joints. It is like a bond in a human body. The joints, we don't have a linear joint, but in robotics we have linear as well as rotary. Each joint provides a degree of freedom. Some of you are maybe familiar with machine tools, CNC machines. So where each axis is moved by a servo motor or a stepper motor. So we call it as axis, but in terms of robotic terms, instead of axis, we call them as degree of freedom, because it is rotational movement also, not just a linear like moves on an axis, but most of the movements of a joint are rotary. So we call them as degrees of freedom. So the robo manipulator consists of two sections, body and arm, for positioning of objects in the robot's work volume. Then there is a wrist assembly for orientation purpose, like our wrist. So at the end of the wrist we have we will have something to hold or something to lift. So the wrist is something that does the job. So similarly, in a robot manipulator, there is a wrist. So it may be a pick and place, a gripper, it may be a welding torch, it may be a paint gun. So there is an end effector that sits on the wrist. So this is a fundamental, these are some of the fundamental configurations by which all the 6 different configurations of robots that you see in the industry are made. So please, if you can just understand this, I think that is all about the various configurations of industrial robots. So there are 2 types of motion. One is translational motion and another is rotary motion. In the translation motion, there is a linear joint type, the first diagram. The symbol for that is L, and there is another is orthogonal joint. We will represent it by O. So it is like a telescope where there is an input link and there is an output link. So the one you can see here on the yellow color is the joint. So inside this joint, the output or link, there is a motion possible, joint motion. In the case of orthogonal, the output link is orthogonal to the input link. So the joint motion is represented here. So the orthogonal joint can move over the input link. So L and O represent linear as well as orthogonal joints, which maybe you can find in some forms of industrial robot configurations like Cartesian, gantry, such forms. Rotary motion. It consists of 3 different types. One is rotational joint. We represent it by R. Twisting joint represented by T, and revolving joint represented by V. So the rotational joint you can see here, there is an input link, there is a joint, and the output link, the joint motion is represented here. It can move up and down. So that is rotational joint. In the twisting joint, the input link is here fixed and the output link can turn or it can be twisted. So in our shoulder, like if you see a human shoulder, the shoulder is fixed, but our the next arm can move in a twisted way, or it may be probably that is revolving joint. Yeah, human the shoulder is a revolving type. Sorry. So that is represented by V. But there are also the cases where end effector moves maybe for orientation, that comes like a twisting joint. So these are the 5 different manipulator joints that are used in industrial robots. We can find only 5 what we have discussed here. There is nothing much more than these 5 in any of the industrial robots that you see in the industry. So the joint notion schemes are L, O, R, T and V. Normally it separates the body and arm assembly from wrist assembly using a column. If there is a body and arm assembly, a column should be used to separate or tell us that one forms a part of the body and other forms a part of the arm assembly. Example TLR, T for twisting, L for linear, R for revolute, T for correct, R for rotational, then T for translational, twisting, and R for rotational. So using TLR or LORTV, we'll be able to, you can just have a look at this picture once again. L is linear, O is orthogonal, R rotational, T twisting, and V is revolving. So if you are asked to sketch some of the manipulator configurations, will you be able to do this? You can try this later. I'll just show the solution also. So TRT colon R, then TVR colon TR, RR colon T. So here you can see, here the base is fixed to the ground. So on top of that there is a joint. So that is twisting. So this rotates, this twists on this. Then there is next joint is R, rotational. Then there is one more twist here. And the next one forms the part of the arm. So that is rotational. So that joint is represented by R. So this will be the sketch or the configuration of a robot with TRT colon R will look like this. A TVR, twisting, revolution, then rotational, then there is a twist, then there is another rotation. So that can be sketched like this. RR, there are two rotational joints, and at the end this is a twisting. So the twist forms a part of the robot arm. So this is how any robot architecture can be represented. So when you go into the design or when you want to understand more about the industrial robots, there are some terms we have to be familiar with. What is the working envelope? Not that all robots can be used for all purposes. So we need to, even if you are asked to select a robot for an application, there are various terms we have to be familiar with. Then another is on the positioning accuracy of the robot. So first is the work envelope or the work volume. How accurate is your robot? Then next is the payload. How much weight it can carry. The weight here means it is the weight including the end effector. So if you are going to have a gripper, the weight of the gripper plus the weight you have to lift, that is called as the payload. The number of axes or the joints. Then the speed of movement, that is also important. Sometimes when you choose robots, we have seen several cases, industries making mistakes while choosing robots. Sometimes they may not be able to achieve the production targets because the speeds doesn't match with the required speed. Finally ends up in a big failure. Then based on the motion control, it can be a path control or velocity control. Then what kind of drive the motor uses? It can be the robot uses. It can be a hydraulic driven, or it can be electrically powered, or it can be a pure pneumatic robot. So all versions are available in the industry. And here the work volume, you can see it's a picture that shows what you mean by work volume. So normal industrial robots are fixed to either the ground or maybe on a table or maybe closer to a machine. So this is fixed. So with the base fixed, how much the robot can reach. So the spatial region within which the end of the robot's wrist can be manipulated, that is called as the work volume or the workspace. This is determined by the physical configuration of the robot. There are 6 physical configurations. We will see that in detail. The size, the number of axes, robot mounting position, limits of arm and joints. And then the end, we are also fitting an end effector. So how long is the end effector? How is the reach of the end effector? That also has an effect on the work volume of the industrial robot. Another term is the spatial resolution. So that is the smallest increment of motion at the wrist end that can be controlled by the robot. So this depends upon various factors, like you have a control system to control the positioning accuracy. We use a lot of feedback systems, so the accuracy of the feedback systems, also the mechanical accuracy of the joints, the drives. So all these contributes to the spatial resolution of an industrial robot. So if you see here, there is a target point. So the accuracy is how far the deviation from possible position to the target point, and maybe the second time you can see the adjacent position, another possible position. So the resolution is the smallest increment. Once you give a command, where it will go and stop. Maybe let us say we want to move it by 1 microns. That is the requirement. When you give a command of 1 micron, the robot is supposed to move 1 micron over on a 3-dimensional space, but it need not come to, because there are no robots with 1 micron resolution or accuracy. Let us say it is the robot's positioning accuracy is 25 microns. Even within 25 microns, let us say we give a command of 10 microns, it may not be going exactly, because its accuracy is 25 microns, so it can be within 20, so plus side 25 or minus side 25. So the resolution here is within the 50 micron range. And the accuracy is the capability to position the wrist at a target point inside the or in the work volume. So that we have seen, that is the accuracy by which within the resolution or within the spatial resolution of the robot, how accurate we can position the end effector. So that is called as the accuracy of the robot. Another very important term is the repeatability, because the robot may have accuracy but need not be repeatable every time. So when you operate it 100 times, if the robot end effector positions at different points during this 100 times of iteration, then its repeatability is very poor. So robots are supposed to give very good repeatability, because we are using most of the cases for repetitive task. So if repeatability is not there for repetitive task, that particular robot may not be a good choice. So here in the first picture, it is not accurate, it is not repeatable, because you can see the 4 points, it is spread across. In the second one, repeatability is there because all points are closer, but it is far away from the point of our actual desired point or required point. So accuracy is less, but repeatability is good. In the third case, it is accurate. At the same time, repeatability is also good, because all the 4 spots are within its accuracy range. So this is another term which is very you can find in most of the data sheets of any industrial robot. And payload, that is the lifting capability provided by manufacturer, that includes the total workpiece weight plus end effector, weight of the end effector, and we also provide a safety range, normally 80%. Then speed of movement, I think we have to speed up. How fast we have to move the manipulators, because sometimes the accuracy may be good, the repeatability may be good, but the robot inherently may be slow. So when you deploy such robots for some fast action like pick and place, packing, so that the productivity will come down then. Motion control, there are path control type and velocity control type. Then drive systems, okay, we discussed this, whether it is electric, pneumatic or hydraulic. And now coming to the various configurations. There are only 6 proven industrial configurations in the market or in industry. First is the Cartesian or the gantry robot. Second is cylindrical, spherical, SCARA, articulated, or parallel robots. SCARA, the notion is here VRO. VRO. So O is orthogonal, R rotational, V is revolutionary. So that is the configuration of a SCARA. Selective compliance, articulated robo arm, assembly robo arm, that is the expansion, sorry. Similar jointed arm robo, except that vertical axes are used for shoulder and elbow joints to be compliant in horizontal direction for vertical insertion task. SCARA robots are having a repeatability of less than 0.25 mm. It's good. Number of axes, normally it comes with 4 degrees of freedom or 4 axes. Vertical motions are smoother, quicker, precise, because it normally holds the job vertically. Good vertical rigidity, high compliance in the horizontal plane. Working envelope is less than 1000 mm with a payload that goes even up to 100 kg, and it is very fast. It goes up to 5 meters per second. Applications are wherever you want precision pick and place, high speed applications like sorting of pins, I mean the connector pins, assembly of lights, LEDs. In such applications, SCARA finds a lot of applications. SCARA robots find a lot of applications. Cylindrical is TLO configuration. There is a twist, there is a linear, and there is one orthogonal. So this consists of vertical column relative to which an arm assembly is moved up or down. The arm can be moved in or out relative to the column. And a lot of these are used in industry with a repeatability of 0.1 to 0.5 mm, minimum 3 axes. Mostly it comes with 2 linear and 1 twisting. Working envelope, it has typically a large working envelope. It has a payload of up to 250 kg, better than SCARA, and the speed is about 1000 mm per second. So speed is not that high as SCARA. But it is simple, but it's some of the small robots are used for precision assembly and large robots for material handling, less machine loading and unloading. Jointed arm is also as articulated. This is most popular types of robot in the industry. It is used in most of the applications. This is how jointed arm will repeatable is in 1.5 axis, minimum 3, go up to 7. It has a develop, is compact, but rigid because there are 5 joints standard, so it is built for long flames. Stability issues will be there. It's so here it tells about 130, but there are robots that can even go up to 1 ton. So you have seen some of the exhibitions or catalogs, or seen some of the videos on YouTube. So applications all in applications like welding, painting, sealing, tubering, material handling, machine printing, inspection. So this is one of the most popular kind of robots in the industry. TRL consists of 1 twist, 1 linear, and 1 rotational. Repeatability in this case is 4. Minimum 3 axes or degrees of freedom. It has but a large work volume, but payload is not as high as articulated, and it is comparatively low speed. So maybe you would have seen the Unimate picture if you remember. That is almost a spherical coordinate robot. But since we have articulated robots with more features and more flexibility available, spherical robots are now not that popular in industries. Cartesian is one linear and two orthogonal joints, consists of 3 sliding joints. It is like a gantry. So it can be used for inspection, precise assembly, arc welding, material handling. Its repeatability is high. It is fast. When we go for a gantry combination, gantry kind of thing, it can also take much more load. Yeah. So when it is used in an industry for heavy lifting of heavy components, material movement over long distances, gantry type of robots are used. In fact, a lot of CNC machines uses gantry type of robots for loading and unloading. And the last one is the parallel kinematic type. This is how it will look like. You can see the work volume here. These are really fast, but mostly for pick and place or packing, like packing of chocolates or sorting of components. And when it comes to the basics of these robotic elements, so we have seen the configuration, the mechanical structure made of links and joints, and various combinations possible. The links and joints, it can be linear, orthogonal, rotational, revolute, twisting. So all these combinations forms the mechanical structure. Now to control this, we need more systems. So every robot comes with a robot controller, and all these degrees of freedom or axes, they are controlled by electric motors or hydraulic solenoids or pneumatic cylinders or hydraulic cylinders. So some kind of an actuator is required, and to actuate the actuator we need power source. So if it is an electrical actuator, the commonly used electrical actuators are stepper motors or servo motors. So stepper motors normally work on open loop, so they are not that accurate. So if you want precision in robotics, then better to go for, if you are planning for electric actuators, then better to go for servo motors. And servo motors requires a closed loop system. So there is a servo drive to amplify the servo system or servo voltage. And there is a feedback that goes back to the servo drive that tells about the position and velocity of the servo motor. And a feedback from the drive is also fed back to the controller. So the robot controller knows precisely where the robot has positioned. So the programming is done using various formats available. But when it is on a special movement, like if you consider a CNC machine, the movements are spread on a table, like it may be a 2-axis or a 3-axis or even more axis, but it is a controlled movement. The table moves on a bed driven by a servo motor, so it can only move linearly. So we can define how much distance it has to move. So it is easy for the controller to make the movement because it is closely monitored, measured, and it is able to position its endpoint. But when it comes to robotics, it is on a space, 3-dimensional space. So if you want to move the end effector by a few mm, it may be using one joint, 2 joints, or more than 2 joints. So combination of movements of joints happen. So writing a program or developing an algorithm for this is one of the tedious tasks in robot control system. So we use the DH metrics, the forward kinematics or inverse kinematics. Either we can tell them. I think those details will be dealt by in the afternoon session by Mr. Winston. He will explain thoroughly about how these equations are written. But fundamentally, you understand that whether how much or how long or at what speed the end effector has to be moved, it is decided by various joints. and there is a control algorithm that goes inside the robot controller, that when you give an instruction either through a lead through programming or teach-in programming method, or there are new programming techniques, they just do a dry run, so it will be able to remember the points. So whatever be the programming style, but the manipulator will be able to make the required position possible through the controller's algorithm. So there is a teach pendant that interacts, that used as an interface between a human operator or the programmer and the robot. So once it is programmed, there is no need of a human. So normally the robot will execute the task that is programmed, and it has a lot of feedback systems to sense that movement is as per the program. And there are various sensors to measure the speed, measure the position, measure the torque, or sometimes the commonness that is gripped by the gripper, so slip sensors. So that is why a lot of tactile sensors are used in robotics. Also vision. Vision is also a very important, vision also has a very important role in robotics, because vision guided movements, vision for picking, placing, inspection. So a lot of applications are there for vision. So that is why we have covered vision also in this program. So this is an overall introduction about the various industrial robots and its architecture. So if you have some questions, you can post it now or you can ask it now. With that, we will wind up. Thank you.
Thank you, sir. I request the participants to unmute and ask the question. Is there any questions from the participants?
And suggestions also. We are all teachers. I am sure some of you will be teaching robotics.